so we were.
All right, well, first I'd like to thank the organizers for inviting me to come to this wonderful place. It's truly astounding to walk outside and see giraffes just before you talk. So anyways, what I'm going to talk about is a project I've been sort of working on with various people over the last few years. In particular, I'd like to point out one person. This is Osman Nazir. He's a graduating graduate student at MIT. He's Barton Zwieback student, and he's very good, and I highly recommend him if you have a job opening. So let me start with some introductory remarks. So localization, as you probably know, has been very successful. So we've been able to do it on gauge theories, on spheres, or other compact manifolds. It's been successfully applied to many situations. So just a few examples is the first. We can start with the first one is the n equals 4 super Yang-Mills, and also n equals, basically n equals 2 stars, say, super Yang-Mills in 4P in Peston's famous paper. And then there's other examples, it's n equal 2 and higher supersymmetries, Chern-Simons, or super Yang-Mills in 3D, by Kapusta, Willett, and Yakov, and also work by Jafaris. N equals 1, 2 super Yang-Mills in 5D by various people, 2, super Yang-Mills in 2D by Bonini and Cremonesi, and also Darude and et al. And even n equals 2, 6D, and n equals 1, 7D super Yang-Mills by Maxime Zagzin and myself. So when, if you look at these papers, you'll see that sort of different techniques are used for the different situations for doing the localization. So, and these techniques are like sort of the more elegant way of doing things is to use index theorems. Okay, but when you use index theorems, it turns out if you're talking about odd-dimensional spheres, say, or even-dimensional spheres, you use a different type of index theorem, basically, to do the computation. Okay, so
Joe, before it's n equal to 6D, you mean 0, 1 or 0, 2?
I need 1, 1.
1, 1.
1.
And you say the second dimension, so the index doesn't care whether there is a superconformity theory or not?
No, I mean, so for example, n equals 2, this n equals 2 star here is not conformal. It doesn't have to be conformal.
But it's non-trivial in the infrared, whereas those two last the 1, 1 and the...
Yeah, these are not super conformal theories.
And they're just trivial in the infrared, right? So it's also in the UV. Nothing special about those theories. Do you see any difference?
Well, I'm not sure I understand the question.
So the 1, 1 super Yang-Mills in 6 dimensions has trivial dynamics. There's no UV fixed point.
Well, I mean, okay, it needs a UV completion. Okay, so there are certain things that are protected by supersymmetry that you expect that your UV completion would be able to measure. So you can measure a free energy, for example, on a sphere. And that's a protected quantity.
And do you go above 7 or you stop at 7?
I'm going to end up stopping at 7, and I'll explain why you end up stopping at 7. So anyways, though, so these different index theorems are used to compute the different theorems, index theorems. And for example, there was a very large review done last year, and there was sort of the introduction of the review. They described how to compute, do the case for odd spheres, which was section 2.3, and for even spheres, it was in section 2.2 about how to compute this. Okay, and the difference is that in the case of odd spheres, when you do localization, you're usually looking for a vector field. And so for odd spheres, you can find a vector field that acts freely, but even spheres, you have to have fixed points. And so that's sort of why you have sort of different different sort of techniques for doing this. However, at the end, if you look at the end, it turns out that the results look very similar to each other. Okay, so you go through this different process and you end up with a result that's sort of similar. So the question that we had is there sort of a more uniform way of doing this for a general d-dimensional sphere? And also, is it possible, if we do, since when you look at these results here, you sort of see like a pattern, and you can write down a formula as a function of d, basically, for, say, the partition functions for these, at least the perturbative partition functions. And so you might ask, is it possible to analytically continue the value of d to situations where it's not actually known how to do direct localization? Okay, so that's what I'll talk about today. Okay, so what I want to do is I'll sort of give a review of sort of a generalized version of Peston's construction. So it would be for super-Yang-Mills on round spheres and their localizations. In this section, I'll tell you why I can't go above 7 dimensions. Then I'll talk about computing one-loop determinants when there are 8 supersymmetries. And then I'll talk a little bit about how to do one-loop determinants for 4 supersymmetries. And then I'll talk about how you can use this to try an analytic continuation from d equals 4 to d equals 3 to d equals 4 when there are 4 supersymmetries. Okay, so a warning. So essentially what we're doing is we're going to basically be doing dimensional regularization for supersymmetric theories. Okay, so this was first, at least in flat space, this was first discussed by Warren Siegel in 1979 about how to do dimensional regularization for supersymmetric theories. And as you can see, it has a lot of citations. At least this was a number sometime in October. Okay, but about a year later, he had a change of heart, and he talked about the inconsistency of doing supersymmetric dimensional regularization. Maybe he went from Harvard to Princeton, and things were a little quieter, and so he had a little more time to think. Okay, it's still cited a lot, but not quite as much as that one. Okay, but at the very end of this paper here, he actually has the following comment. The general difficulties described above for analytic dimensional reduction seem somewhat paradoxical in light of the fact that it has worked so well, with the possible exception to triangle anomalies. So this will be our philosophy. Maybe there's a problem, but it seems to work, so I'm not going to worry about it. All right, so let me review a little bit about Peston's construction. So let me first start off with 10-dimensional flat space Lagrangian, super-Yang-Mills. Okay, and so the Lagrangian has a very simple form. It's just f squared minus psi d slash sub. And I'm going to sort of follow Peston's sort of conventions where he doesn't have a factor of I in front of here. Okay. So anyways, this action is invariant under supersymmetry transformations. So the transformation of the vectors is just epsilon times gamma psi, where epsilon is a bosonic real chiral spinor. Okay, so if the index is up, okay, it's 1 chirality, it has a spinor with say positive chirality. If the index is down, it's with negative chirality in 10 dimensions. Okay, and then the transformations back from the spinors to the transformations on the size is proportional to Fmn multiplied by this combination of gamma matrices like this. Okay. So we're going to use tildes and untilde gamma matrices. If it's untilde, the indices are down. If it's tilde, it's up. Their indices are up. Okay, so then the first thing you want to do if you start with 10 dimensions is you want to dimensionally reduce it. Okay, and we're going to dimensionally reduce it to a Euclidean gauge theory. And so what we're going to do is we are going to assume that dimensions 1 to d, okay, are going to be our space-time part. Well, I should, okay, but we're assuming that our space-time part is actually Euclidean, so it's just the spatial part. And then the other dimensions will become our internal dimensions, if you will, the parts that we're dimensionally reducing, and so these will become scalar fields. Okay, and the time-like direction that I had up here is actually going to correspond to the direction of a scalar field. So the scalar field sort of going to be labeled by 0, and then d plus 1 up to 1. Okay, and then the derivatives along compactified directions are 0, so that means that if we have a cross term for our field strength, it's really a covariant derivative acting on a field phi, and Fij is just the commutator of phi I and phi j. All right, so since I did this somewhat unusual dimensional reduction, okay, the scalars actually transform under a vector representation of SO1 comma 9 minus d. Okay, so this is the R symmetry in flat Euclidean space, and phi naught has a wrong sign kinetic term. Okay, eventually we'll sort of fix that wrong sign kinetic term, but for now it has a wrong sign kinetic term. And then the d-dimensional coupling just comes by taking the 10-dimensional coupling and dividing it by the volume of this reduced space. Okay, so now let's put the theory on a sphere. Okay, and so I'm going to choose these projective type coordinates, so just ds squared is just dx squared divided by this factor of 1 plus beta squared x squared squared. And I'm going to use beta because this factor of 1 over 2r is going to appear all over the place, so I'll just call that beta. I'm assuming the radius of the sphere has radius r. And if we were to, say, be in 4 dimensions, we know then we reduce to n equals 4 super Yang mills. And in 4 dimensions, this gauge theory is superconformal. And so we have to add a conformal mass term to the action, which looks like this. It's a trace of phi squared divided by 2 over r squared. All right, now if d is not equal to 4, it's no longer conformal. Okay, but we're going to include a similar sort of term in our action. Okay, so it'll be a trace phi squared. And for convenience, we're going to pull out a factor of little d. The d is the number of dimensions we're reducing to. And we will allow for a delta I where the delta i's are not necessarily the same for each of the scalars. Okay. So delta I, in a sense, is the analog for the dimension of phi I, but it's not really the dimension. In fact, it won't be the dimension. All right, now we actually, so this term here is enough if we're in 4 dimensions. Okay, but if we're not in 4 dimensions, we need additional terms in order to preserve this supersymmetry. Okay, so to find those additional terms, what we should do is actually look at the conformal killing spinners. And so for conformal killing spinner, supersymmetries, we have the following sort of equation that if we take up a spinner and take a covariant derivative on it, it should come back with an opposite sign, an opposite chirality spinner, so I'll call that epsilon tilde, multiplied by a gamma matrix. And then if we take the covariant derivative on that epsilon tilde, we get back the original epsilon, okay, multiplied by a gamma matrix, and multiplied by a factor of minus 1 over 4r squared. Okay, so the general solution to these equations, okay, on the sphere, okay, for any dimension d less than or equal to 10, okay, here's the metric again, is that this epsilon is equal to 1 over this factor here to the 1/2 power, okay, times a constant spinner epsilon s plus x dot, a gamma matrix, times this other chirality, another constant chirality matrix epsilon tilde. Okay, so epsilon s and epsilon tilde are arbitrary constant spinners, so there's 16 of each of them. Okay, so there's 32 independent conformal killing spinners. Okay, now if d is not equal to 4, there should only be 16 supersymmetries, not 32 superconformal symmetries. Okay, so we need to reduce, we're going to reduce to 16 different spinners by further imposing the following. We're going to say that epsilon tilde is equal to this constant beta, remember beta is 1 over 2r, times a matrix lambda, okay, and in order for this to be consistent with this, okay, if we take a gamma tilde times a lambda, if we change the order, this becomes a minus lambda tilde times a gamma mu. Okay, so this thing basically has to anticommute with that. Not only that, we have to have that the square of these two is equal to 1. Okay. And also, another condition turns out, if d is not equal to 4, we have to say that these lambdas are antisymmetric. I should also say that all the gamma, in this particular basis, I can choose a basis where the gamma matrices are symmetric and they're real. Okay, so we assume that they're symmetric and real, Okay, and so this lambda tilde, this lambda transpose here has to equal minus itself.
These are still gamma matrices of 10 dimensions?
Yeah, these are 10-dimensional gamma matrices. Okay, so you need to choose a lambda. Okay, and the simplest choice for a lambda is to choose a lambda with 3 gamma matrices. Okay, so I'm going to choose them, okay, such that lambda is equal to gamma 8, gamma tilde 9, gamma 0. Okay. And in which case then I should also say then with this condition then that the relation between these constant spinners here is that the epsilon tilde c is equal to beta lambda times epsilon s. So anyways, you can see that this construction is going to work for spinners up to d, it's going to work for spheres up to d equals 7. Okay, because the components along the sphere are the mu, okay, and they have to anti-commute with this lambda. Okay, so gamma 8, gamma 9, and gamma 0 won't anti-commute, they'll commute with the lambda. So that's why we can do this up to d equals 7. Okay, so then we also have to do a slight modification to the supersymmetry transformation. So remember in the first slide I said that the transformations on the AMs was just given by this part here, and the transformations on the sides were given by this first term here. But once I put it on the sphere, I have to add an additional term here, okay, which is proportional to this covariant derivative acting on epsilon, multiplied by this combination of the scalar field and these gamma matrices here. Okay, and it turns out then that you need to set these guys, these constants that appear here are actually depend on what the value is of I. And so if you choose I to be 8, 9, or 0, so in that case I'll call that a capital A, okay, then alpha equals this, depending on the dimension. And if I is not any of those 8, 9, or 0, but all the other possibilities, then it's equal to 4 with D. And then this coefficient delta A that appeared in the action that was multiplied by the trace phi squared term, okay, for the A indices 8, 9, 0, it's equal to alpha A, and for the little I indices, it's equal to 2D minus 2 divided by D. Okay, and then with some work, you can show that the complete maximally supersymmetric Lagrangian on the sphere has this form. So this was the original part. Okay, then we have, well, and let me just go through and say a little bit about each of the terms. You notice it generates sort of what looks like a mass term for the fermions here, so d minus 4 over 2r. Okay, you have what looks like a mass term for the scalar fields. Okay, so the scalar field, so depending on the index, 8, 9, 0, you get this coefficient, and for the little I, you get this coefficient. And then there's also this cubic term that's proportional to this term here. And you can see that actually we preserve 16 supersymmetries by doing this, but the R symmetry is explicitly broken unless D is equal to 4 or 7. Okay, so in D equals 4, remember super Yang-Mills, N equals 4 maximally supersymmetric. Yang-Mills has an SO6 R symmetry. Well, that's still preserved because if D is equal to 4, you can see that this coefficient is the same as this coefficient, and this term is 0. So you still have a full SO6 rotational symmetry amongst the scalar fields. Okay, but if D is not equal to 4, these coefficients here are different. Okay, so that rotational symmetry is actually broken. Okay, and so it's broken actually to SO1 comma 2 times SO7 minus D. Basically, you can rotate among the capital A indices, and you can rotate among the little I indices. Okay, and those are those two. Okay.
How do you take into account the different behavior of gamma matrices in different
I'm sorry, I didn't hear the question.
The behavior of gamma matrices in different dimensions?
I'm still sort of assuming these are like 10-dimensional gamma matrices. So I always write the gamma matrices in 10-dimensional gamma.
So there's no coupling between scalars and fermions, or is it part of the split side?
Yeah, it's sitting in here.
So there are your normal Yukawa couplings.
Yeah, they have the Yukawa couplings.
But for D equals 4, you don't need, for D equals 4, you don't need to do all this game, right? I mean, for D equals 4, you have
Yeah, no, so D equals 4, this term here is precisely the conformal mass term. Okay, and this extra term I added in is not here, and this term is 0, so it's not here. So you just have that term, and these two terms are the same. So you get that.
And for D equals 7, how do you see that you get?
Yeah, so D equals 7, the reason why you don't break anything is because S equals 7 minus D is trivial. So there's no little i's. So there's no breaking.
But what about the last term?
This is still invariant under SO1, comma 2. Because it's proportional to like an epsilon tensor. Yeah, it's completely antisymmetric. So it gives it. Sorry. Oh, okay. All right.
So how is supersymmetry restored, even if it's not manifestly supersymmetric?
It is supersymmetric. So under these transformations, this term here is invariant, or up to total derivatives. So this choice. Okay, I skipped a ton of details. So, but this choice here is chosen so that it's invariant under these transformations.
But you say that our symmetry is broken.
Yeah, it's our symmetry.
Supersymmetry is 16, right?
Yeah, but there's still 16 supersymmetries. And this is actually consistent too with, so this is consistent with the supergroups too. So for example, in the 7-dimensional case, you have an SO8 rotational symmetry on the 7 sphere, okay, and you have an SO1 1 comma 2 for the R symmetry parts, and you know that there's a superalgebra that's OSP 8/2, okay, and so that has 16 supersymmetries, and the 2, okay, that's assuming that's compact, but this is sort of the non-compact version, for example. And every other case, and in the 6-dimensional case, you have an SO7 and an SU2, and an SU2 subgroup, okay, and that fits into this funny F4 superalgebra. Just a different, different choice of the signature on these rotations that you normally. In fact, basically for any sort of superconformal algebra, there's sort of one of these. I mean, superconformal algebra that you normally run into, like so in 60, you can have an OSP 8/2, which is a 1-0 SCFT, and that sort of is the one that sort of maps into this guy.
And these modified supersymmetry transformations, the closed off shell?
I'm coming to that, okay. Okay. So in 2 slides. So anyways, this was a way to construct things with 16 supersymmetries. But if D is small enough, we can reduce to 8 supersymmetries. So it's small enough in our case if D is going to be less than or equal to 5. Because in that case, then we can choose, if D is less than or equal to 5, we can choose a combination of gamma matrices when we're going to need 4 of them. Okay, so we can sort of reduce our allowed values of epsilon by factor of 2, by imposing that if I take gamma 6, 7, 8, 9 and act on an epsilon, it's equal to plus. Okay, and then my spinner psi splits into 2 different spinners, psi and chi, where psi is even under this combination of gamma matrices, and chi is odd. Okay, and you can see you need 4 if you square this. So anyways, then, in terms of the 16-dimensional language, in terms of the maximally supersymmetric language, your fields split into a vector multiplet and a hypermultiplet, where the vector multiplet is made up of the gauge fields and these parts of the little size, and also the scalar fields that are either 0 or d plus 1 up to 5. And then, or there are hypermultiplets which come from the chi and the rest of the scalar fields where they go from 6 to 9. Okay, so you can see that this thing has 4 scalar fields in it, and this is the corresponding fermionic particles to that. And then once I assume that my epsilon satisfy this, okay, I can reduce, since I reduce the number of supersymmetries my action has to be invariant under, I'm allowed to change things a little bit. Okay, in particular, my constants alpha I can be modified by a mass term, which I call this part inside here. And the sigma I is basically a sign, okay, depending on whether or not I is 6 or 7, or it's 8 or 9. Okay, we can have this term, and the delta i's get modified by this amount. The other alphas and deltas that are not 6, 7, 8, or 9 don't get changed. Okay. And then this mass term I had in my Lagrangian, okay, that can split into this term for the vector, the fermions in the vector multiplet, and then a mass term for the hypermultiplets. And finally, this cubic term here, this can split into a mass term, into something where you have a commutator of phi 0 with 6, 7, and a commutator with 8, 9. Okay, so in particular, if I set the mass to be a particular value, okay, this term goes away, and I choose the value so that the mass is basically minus 1 over 4i times this term here. Okay, this term goes away, this term becomes what I had before with 16 supersymmetries, and then this term here, this coefficient here becomes the same as this coefficient. You go back to the supersymmetry case. So you can see actually that unless d is equal to 4, to enhance the supersymmetry, okay, normally in flat space, okay, if you had a hypermultiplet, you want to set its mass to 0 to enhance the supersymmetries. Okay, on the sphere, okay, they're actually not quite 0. They're actually, it has to be, if d is not equal to 4, it has to be non-zero.
Just a quick question. Normally these expressions they have a limit which one argues to infinity, which is very nice. What's happening when the sphere compactifies?
Yeah, then it goes. Then
what the deltas? The delta are.
yeah. So if you do, yeah. So if r goes to infinity, basically then this term here becomes proportional. The dominant term. Okay, these terms and these terms here say are subdominant. You get m squared times r squared. You remember that in my original term of my action, the delta was multiplying a 1 over r squared. So the r squared cancels off, and you're left with an m squared term.
Oh, nice.
So that all works. Yeah. Okay, and if d is less than or equal to 3, okay, you can reduce to 4 supersymmetries, okay, because not only can I impose that epsilon is equal to this combination of gamma matrices times epsilon, okay, but I can take another 4, so these 4 combinations, and set that equal to plus epsilon, in which case then, this should be a capital psi here, psi splits into a psi, and then a chi1, so the vector, oh actually no, it shouldn't be. This was the vector, the 8 supersymmetry vector multiplet splits into a 4 supersymmetry vector multiplet and a chiral multiplet, and then the hypermultiplet splits into 2 chiral multiplets. And then the thing is that these combinations of gamma matrices give plus plus for the size, and then plus minus minus plus or minus minus for the different chi's.
The dimensionology of this thing is the same as for normal difference, I guess. If you want to obtain a theory which has so many supercharges to go to so many dimensions, I mean that's.
Wait, say that again?
The dimensional, I mean the way the dimensions work, okay, of course the Lagrangians are different, but if you just look at, filtering into a space, you have this.
Oh yeah. No, this is all, yeah, absolutely.
Okay.
And then we can also we're allowed, since we only have 4 supersymmetries, we're allowed to tinker even more with these alphas, and we can give sort of individual masses for these different for the different chiral multiplets here. And so we modify this alpha and this delta accordingly. Okay, now one thing I should say, and this actually caused us some confusion for a while, is that the masses that show up in here, okay, are actually what are known, since this is d less than or equal to 3, you know that in 3 dimensions you can have what are known, you can either have real masses or complex masses, and it turns out that these are the real masses. Okay, and I'll explain this in a bit in the next slide. So
there is a difference between entering the BPS central charge.
Exactly. So yeah. So first of all, before explaining that, so supersymmetry, it turns out I actually don't have quite as much freedom as you would naively think. Okay, supersymmetry actually requires that this combination of the masses and beta and this term here, the sum of these things has to be equal to 0. And to understand that, in n equals, so let's forget about being on a sphere. Let's suppose we're in flat space. So in n equals 2 flat three-dimensional space, okay, the thing is that what Ami's just saying is that real masses appear in the superalgebra. So they're basically central charges, okay, while complex masses are in the superpotentials. Okay. Now, if you start with the maximally symmetric, supersymmetric Yang-Mills, there's a term in the superpotential. If you write things in terms of n equals 1 language, there's a term in the superpotential that looks like trace Qi, Qj, Qk with an epsilon ijk term. And if you act with this combination of Qa and Q tilde and Q bar, okay, on this term, okay, this will give you a term that's proportional actually to the sums of these real masses of these charges. And there's some okay, and so for this term to be supersymmetric, so in order for the action to be supersymmetric, the sums of these m's has to be 0. The sums of the real masses has to be 0. Okay, so this term up here, this is sort of the generalization to the sphere. So this beta, remember, is 1 over 2r, so if r goes to infinity, this goes away, and you're just left with the real masses part. Okay, but being on the sphere, it's actually not that their sum is equal to 0, but their sum is equal to a little bit.
So this is just happening in n equals to r. This phenomenon is not happening on the sphere, right?
This is not just the sphere. This is if you try to turn on these masses. Okay, you have it turns out normally when you do a mass deformation of maximally supersymmetric Yang-Mills, you don't change the couplings, the individual couplings. You can change the individual couplings. That's what like Lee and Strasser do and things like that. But if normally what we call is like n equals 2 star or n equals 1 star, you don't change the couplings. You just put mass terms for either the hypermultiplet or the chiromultiplet.
I see. But what's the constraint in that case?
In the 3D case, this is the constraint. Okay. Well, this real masses only appears in 3 dimensions, or less. Okay, in 2 dimensions, these are the twisted masses that on is talking about.
So
yes.
in 3D,
oh, sorry.
No, I'm just confused. So in 3D, so if I just take 3D angles and I get masses, these terms will how they look like. I mean, if I just take 3D angles with all the
Your field has no method.
No, sorry. Yeah, maximum supersymmetric angles. The theorem works on the 2 branes, for example. If you just take maximum supersymmetric angles in 3 dimensions.
Well, okay, so maybe a way to think about it is, suppose I did it in 4 dimensions. Suppose I'm starting in 4 dimensions.
Okay, very good.
Okay, so when I compactify on to 3, so then I compactify down to 3 dimensions. So one thing I can do is I can sort of turn on a Wilson line that goes around that circle. And that's basically contributing to those real masses.
Okay, so they're not the normal masses of n equals 1.
No, they're not the normal masses. So in the normal masses, in n equals, okay, so in the 4D case, masses just in the superpotential. Okay, and they just descend down, and masses in the superpotential just descend down. Okay. And then
you have a background vector multiplet.
Yeah, it's basically a background vector multiplet. So if you have a global symmetry, you can turn on a background vector field. And that vector field you can think of as a Wilson loop going around there, and that gives you the mass.
Great.
Yes?
This n equal to 3D superalgebra with that mass term, is this a generic feature in the sense that like n equal to 4, for instance, in 3D, or like there are these algebras where the mass appears with the R symmetry there?
So you can this is a general, okay, so this is a general feature if you assume that I have this term in the superpotential. Okay, because I'm saying that I'm assuming that I'm not changing, I have a coupling here. Okay, if I didn't have this term, then this constraint isn't there. But you're right. So normally when you write things down, you have the R symmetry part and then the real mass part. Okay, and the R symmetry part is basically the imaginary part of this real mass. So on the sphere, these real I call them real masses, but they're not necessarily real. Because one part is this R symmetry charge, basically, and the other is a real mass. So, did I answer your question, sort of? Or?
Yeah. So there is here Q bar is the P plus the real mass times the epsilon. So what I had in mind is that in the n equal to 4 and higher cases there is the R symmetry part.
Yeah. So right. So that okay. So in a sense, that's in. So setting this equal to 0. If say we're doing n equals 4 super Yang mills. Okay. Setting this thing equal to 0, say, you're going to see that this mass here. Okay. You can't say all the masses are 0 because you don't balance off that term. Okay. So that term is sort of contributing to that R symmetry part there. Okay, so anyways, okay, now finally getting to the off-shell formulation. So then we want to, so you know that for 16 supersymmetries there's no complete off-shell formulation, but for localization it turns out we don't need all 16 supersymmetries, an off-shell formulation for all 16 supersymmetries, and basically only need it for one. Okay, and so we're going to choose our epsilon here so that we get a convenient vector field. Okay, and the vector field we construct by sandwiching a gamma matrix between these two epsilons. And you can show that these vector fields, okay, that when contracted with each other, it's equal to 0. Remember, I have one time-like direction, okay, which is the V0 direction, but remember V0 corresponds to a compactified direction, okay, but that means the uncompacted, and we're gonna sort of normalize this this epsilon such that V0 is equal to 1, okay, so that means the inner product of all the spatial directions, okay, is equal to 1, including the compactified directions. And it's convenient to choose this vector such that the 8 and 9 components are equal to 0. Okay, so to go off shell, what you normally need is auxiliary fields. Okay, and so we're going to have auxiliary fields Km. We're going to have 7 of them. M is going to run from 1 to 7. And we're going to also have introduce 7 more spinners, M. Okay, so this is a particular epsilon, one of those 16. Okay, and so these new M's are chosen such that they have this orthonormality condition with themselves and with the epsilon. Okay, in other words, if I sandwich a gamma M between an epsilon and the new M, okay, it's equal to 0 for all 10 components of M. And if I sandwich a gamma M between these two guys, if M is not equal to M, I get 0. And if M is equal to N, I get the same thing as I would for epsilon. Okay. So then, when I go off shell, it turns out it's very simple to go off shell. Okay, so this part here, inside here, this was my original supersymmetry transformations. And all I have to do is to add to the transformation on psi a term which is Km nu M. And the transformation on Km is equal to minus nu M times this combination of psi's inside here. And you notice that this term here, okay, if I set that equal to 0, that's the equation of motion for psi. Okay, so the transformation on Km is equal to 0 on shell. Okay, and then the only other thing I have to add to the Lagrangian is an auxiliary term which is just proportional to trace of Km, K. Okay, multiplied by the factor of 1 over G squared. Okay, that's all I need to do. And so then you also have to make sure that the algebra closes within the symmetries of the theory. Okay, so if you do 2 transformations on A mu, okay, you see that you get a Lie derivative plus a gauge transformation. Okay, so that means a Lie derivative is good, so it means it can translate on the sphere. That's a symmetry of the sphere, so that's fine. Similarly, if I do a transformations on the phi I, okay, you can see that you'll still get a Lie derivative along the direction of the vector field, I should say. Plus the gauge transformation, that term here, it's the same gauge transformation as you have there, the corresponding one. And plus this term here, which is actually just an R-symmetry transformation. And you can see that it turns out that the R-symmetry transformations that you're doing are within the R-symmetry transformations that survive, namely the SO1 comma 2 cross SO7 minus D. Okay, so this is a good transformation. So these things close inside the algebra, and you can show the same for the size and the case. Okay, and there's straightforward modifications when adding mass terms. Let me not do that.
So you have this explicit vector, right?
Yeah.
New. So is the formula covariant somehow, or break somehow? Or
Sorry?
You've taken some values for this new.
Yeah, new is something else. Yeah.
Okay. Yeah. But is it Lorentzian variant or?
Well, I've chosen I could choose basically. Okay, I've chosen a particular one. Okay, but I could have chosen any one I wanted. Okay, so the actual.
But in the intermediate stages, you don't have full SO, D, or T plus 1, whatever covariance.
Yeah, that's right. Because say my epsilon, if I could choose where it has a component, say along the phi 6 direction.
Mm-hmm.
Okay, and so then that's not invariant under
Some rotation.
some rotation, but it does a rotation on it.
But is it somehow this usual trade-off that to go off shell you have to break?
Yeah, it's the usual trade-off. That's it. So if I could do it, yeah. So if I could do it for everything, okay, then I'd have an off-shell formulation for 16 supersymmetry.
Yeah, which of course.
Which is
just somehow like on that cone or something.
yeah, exactly, right. Yeah. Okay, so now we want to localize. Okay, I might have to speed up a bit here. So we have a partition function, and what we can do is we can add, and so this phi here represents all fields in the theory of e to the minus t of s minus t times q acting on something, and q is some fermionic symmetry generator, and I'm assuming that this qv is positive definite. Okay? Since this is fermionic, you can basically show that assume this is a symmetry basically. You can show then that this partition function doesn't depend on t. All right, so then since it doesn't depend on t, you can take t to be infinite. So basically it localizes onto the fixed points of qv. Okay. Basically where qv is equal to 0. Because if qv is not equal to 0, then this thing is exponentially suppressed. Okay. So it localizes onto fixed points of v under this cube. And so my partition function then, I can write as a sum over all these different fixed points of e to the minus sk, where sk is this s here evaluated at each of those at the kth fixed point. And you also have to take into account a determinant factor when fixing to this thing, because you still have this integral over all the fields, and so that can contribute to a determinant. And so there's a corresponding determinant that goes along with it. Okay, so you can choose your Q. So for Q, we're going to choose delta epsilon, so our supersymmetry transformation. And for our V, we're going to assume that it's psi del of the bar of D acting on psi, delta acting on psi, where I'm defining this bar del psi as basically this term here. So this is basically d psi here, okay, with a gamma naught stuck inside there. And this extra term here, in the other case, for just d psi, I had a plus sign, so I'm actually going to change it. You can't really tell here, but that's red to indicate that I've changed the sign. But that's what I mean by d psi bar. Okay, so then if I pick out the bosonic part of d epsilon psi, okay, the bosonic part then is just d psi d bar psi, okay, because basically acting on, you pick out, when d acts on this, you get a d psi, and then you have times this d psi bar part here. Okay, so you're going to get a term like that. Those are going to correspond to the bosonic part. The fermionic parts are going to correspond to psi d then acting on the second part here. So you have a fermion here, and this term here will be a fermion. Okay, so if you look at those terms, what you find is that you get an f squared term, you get an f tilde-like term, okay, with this combinations of gamma matrices inside there. Okay, we're not gonna worry about these too much. You get this combination of terms here. Okay, I'm mainly gonna concentrate on this last term here. So you're gonna get the auxiliary fields, okay, plus this combination of phi 0, and this whole thing here is squared, and then all the other scalar fields besides the 0, okay, you're gonna come with a phi squared term multiplied by this coefficient here. Okay, so so if we assume that we're in the large n limit, then we can sort of forget about instantons, and so that means our gauge fields are gonna be 0, okay? So the only thing then, we can forget about, say, most gauge field configurations and just worry about the scalar field configurations. So just worry about like these two terms down here. Okay, so we want this thing to be a minimum, so that means that the phi j's have to be set to 0 if j is not equal to 0. Now we want this term to be a minimum, but you notice there's actually a wrong sign here. And this is because, remember I started with this wrong sign kinetic term. Okay, but what I can do is I can just do, say, a Wick rotation, such I set the auxiliary fields to IKs and phi naught to I phi naught. Okay, so going back to my original action, it gets changed to the right thing. And so to set this thing equal to 0 then, we have to set the km's equal to this. Okay, and you notice that this is not actually, this is not the odd-shell solution to the equations of motion. So localization, as a common theme of localization, is that you're off-shell. You get an off-shell configuration. Okay, now there's actually kinetic terms for this phi naught that are sitting inside this f squared term. Okay, and so for this thing to be minimized, okay, these phi naughts have to be constant. Okay, so if we take this result and we substitute it back into that Lagrangian I wrote down before, you find that at the fixed point, you get something that looks like this. Okay, and this is true for any value of d, assuming d is less than or equal to 7. So if I look at my different,
The fermionic part just goes away.
yeah, fermion part won't go. The fluctuations for the fermions are of course important, but those go away. Okay, so if I look at the fixed points, so just as an example, if I look at the action at this fixed point, so I should get, since the phi's are constant along the sphere, I can just multiply by the volume of that sphere, so the Vd times the Lagrangian at that fixed point. And if I define the dimensionless variable sigma, okay, which is equal to r phi naught, okay, then I find that at the fixed point I get something like this. So for example, for d equals 3, you get that this is 0. Okay, and so you can understand that because you know that in 3D, the 3D Superyang-Mills Lagrangian is Q exact. Okay, so it shouldn't be contributing anything to the partition function. Okay, so it doesn't actually make a contribution. Okay, so for d equals 4 then, okay, you get this is Peston's result. Okay, this is d5, this is Zabzin and Kim's result. Okay, d equals 6 and 7, this is our result. Okay, you get these results here.
Are these some special values that you can compute for innovation?
What's that? Yeah, well, I can compute it at any dimension. And these are the examples, but if I actually substitute it in. Yeah. So here there's no problem in, as far as the action is concerned, there's no problem in